Now that we have laid the foundations for statistical process control, let's spend a little time talking about some of the key mechanics behind implementation of these tools. Implementation of control charting should be done only when needed to ensure the proper performance of the process. While this creates peace of mind and a sense of robustness, it can be highly burdensome for the operator. The process takes a back seat at the expense of monitoring and testing. I am sure we can all think of a process in our society that is so overwhelmed with testing and oversight that the true aims and purpose of the enterprise has become clouded and ineffective. Monitoring everything really means we monitor nothing. Indicators go ignored, and the benefit is lost as costs mount. Some considerations for the selection of a control chart variable include safety issues, environmental variables, areas with high defect rates, critical process variables that contribute to internal costs and process capability or trigger customer complaints, regulatory items, or items that are requested by the internal or external customer to help control the process. Much like we characterize processes in terms of a critical path, we hope to find that one critical process variable from which all other variables depend upon. If we can find this one variable, monitor and control it, we can truly understand how to affect the process. Tools such as design of experiments, Pareto, and ANOVA can be useful in finding these vital few or one. Control charting allows us to assess part-to-part variation consistency within an average variation of the sample. To facilitate this, observations are placed into rational subgroups. Our ability to glean useful information depends on the makeup of these subgroups. Subgroups are selected in a way that makes each subgroup as homogeneous as possible, and such that the maximum potential for variation from one subgroup to another is realized. Selection does depend on our knowledge of the components of the total process variation. It is very important to maintain the order of production in charting. A process found to be out of control can be reordered to show very strong control. In essence, chance causes and assignable causes are intermingled to create these results. When ordering based on production, we can subgroup under some different approaches. In time-based subgrouping, changes in the process average can go undetected if corrected before the next subgroup is taken. Subgrouping based on the time of production is used to minimize the chance for variation within a subgroup and maximize the chance for variation from subgroup to subgroup. Representative state subgrouping can be preferable when our aim is to determine acceptance of the product. We subgroup based on the state of production over a given period of time. A random sample is chosen from all the product made since the last sample was taken. Subgroup size is driven by our desire to minimize chance variation within a subgroup. For this reason, 5 subgroups of 5 would yield far more informative results over one subgroup of 25. Larger subgroups tend to exhibit more likelihood for a process change within the subgroup. Subgrouping can be facilitated through standard sample procedures. We would never want to create subgroups that consist of dissimilar items. Sometimes this may happen without our knowledge. We subgroup with the intent of minimizing variation within while maximizing the variation between subgroups. Every process will have common cause variation or noise. We handle noise by averaging across it as opposed to across the signals. When we make a decision error, this is considered a type 1 error. This would be characterized by a situation where a remedy was applied to a process variation when the variation was actually random. As our control limits increase, we decrease the probability of a type 1 error. We must be cautious though. If the control limits get too wide, our probability of a type 2 error will be intolerably high. This is why we settle on a plus or minus 3 sigma interval. As the subgroup size increases, the control limits will move closer to each other. While this increases the sensitivity of the chart to small changes, it reduces our propensity for a type 2 error. In general, we should aim for a subgroup size of 2 to 6.